Hey everyone, welcome back to Chem Story. Today we're diving into another key reaction, intermediate in organic chemistry, carbon ions. These guys show up in all kinds of reactions, from nucleophilic substitutions to enolate chemistry. And here's the thing. Once you understand how carbon ions form, what they look like, and what makes them stable or unstable, you'll be able to predict reaction mechanisms more confidently, and even design better synthetic routes. Let's get started. So, what exactly is a carbon ion? It's a reaction intermediate where a carbon atom holds a formal negative charge. Now, we usually think of carbon as making 4 bonds to fill its octet, right? But in a carbon ion, the carbon only makes 3 bonds, and it also holds onto a lone pair of electrons. That gives it 8 valence electrons total, so it still has a full shell. But here's the catch. That extra lone pair makes it very electron-rich. And that's why carbon ions are highly nucleophilic. They're naturally drawn to electron-deficient species, or electrophiles, and they're ready to attack. All right, let's talk about how carbon ions are classified. There are 2 main ways we break them down, by hybridization and by how many groups are attached to the negatively charged carbon. First, hybridization. Most alkyl carbon ions are sp3 hybridized, so the carbon has a tetrahedral shape, with the lone pair sitting in one of the sp3 orbitals. Now, if the carbon ion is on a double-bonded carbon, that's a vinyl carbon ion. These are sp2 hybridized, which gives them a trigonal planar shape. And because sp2 orbitals have more s character, they hold the negative charge closer to the nucleus. Then we've got acetylide carbon ions. Here, the negative charge is on a triple-bonded carbon, and that carbon is sp hybridized, giving it a linear shape. With 50% S character, that negative charge is pulled even tighter toward the nucleus, and that actually makes acetylides the most stable of the bunch, based on hybridization alone. Now, carbon ions can also be classified by how many alkyl groups are attached. A methyl carbon ion has none. Primary means 1 group, secondary has 2, and tertiary has 3. These structural differences don't just change how carbon ions look, they also affect how reactive and how stable they are. And that brings us to the next part. Let's break down the main factors that really control carbon ion stability. So, what actually makes a carbon ion more stable? There are 3 major factors. Let's start with the first one, inductive effects. This is also called a sigma withdrawing effect. If there's an electronegative atom nearby, like fluorine, chlorine, or a nitro group, it pulls electron density away from the carbon ion, and that helps reduce the buildup of negative charge on the carbon. So the negative charge gets a little help, and that makes the whole thing more stable. Now, the second factor is resonance. If the negative charge can be spread out over more than one atom, that's a big win for stability. A great example of this is enolates. In an enolate, the negative charge isn't stuck just on carbon. It's delocalized between the oxygen and the carbon. And that sharing of charge makes the entire system much more stable. The third factor is hybridization. More specifically, how much s character the orbital has. The higher the s character, the closer those electrons stay to the nucleus. And that makes the carbon ion more stable, because the negative charge is held tighter. Let's look at the trend. sp3 hybridized carbon ions, like in most alkyl systems, are the least stable. sp2 is a little better. And sp hybridized carbons, like in acetylides, are the most stable, thanks to that 50% S character. And here's why that matters. Less stable carbon ions, like those with sp3 hybridization, are highly reactive. They're eager to find something to react with. But more stable ones, like sp hybridized carbon ions, are more selective. They don't just react with anything, they pick their spots. All right, now let's take a look at some real reactions where carbon ions play a central role. Carbon ions aren't just theoretical. They show up in some of the most important reactions in organic chemistry. They usually act as nucleophiles or bases, and they're essential for building carbon-carbon bonds. Let's start with a big one, organometallic reagents. We're talking about compounds like Grignard reagents, RMGX, and organolithium reagents, RLI. These are made by reacting alkyl halides with magnesium or lithium metal, usually under dry anhydrous conditions. And even though the carbon is technically bonded to the metal, it behaves just like a carbon ion, meaning it's strongly nucleophilic and ready to attack. Grignard reagents, for example, react with aldehydes and ketones to make alcohols. Organolithium reagents can do that too, but they're even more reactive, so they're also great for deprotonation or tougher nucleophilic additions. These kinds of reagents are incredibly useful tools, especially when you need to form new CC bonds in synthesis. Another key reaction involving carbon ions is the formation of acetylide anions. These come from terminal alkynes, which can be deprotonated using a strong base, like sodium amide, NaNH2. Now here's why that works. Terminal alkynes are more acidic than alkanes or alkenes, and that's because their carbon is sp hybridized. That high S character pulls the negative charge closer to the nucleus, which helps stabilize the carbon ion. Once you've got the acetylide anion, it becomes a super versatile nucleophile. It reacts with alkyl halides via SN2 mechanisms, and that's great for extending carbon chains. It can also add to carbonyl compounds like aldehydes or ketones, forming propagyl alcohols, which are really useful building blocks in synthesis. So yeah, acetylide anions are small, but powerful players in carbon-carbon bond formation. One of the most important places we see carbon ions in action is in carbonyl chemistry, especially when we talk about alpha hydrogens. The hydrogen right next to a carbonyl group, the alpha hydrogen, is actually a bit acidic. And that's because when you remove it, the resulting carbon ion is stabilized by resonance with the carbonyl. To make that happen, we usually use a strong base like LDA. That's lithium diisopropylamide. It pulls off the alpha proton, giving you an enolate ion. And that enolate? It's a total game changer in synthesis. It shows up in reactions like the aldol condensation, where two carbonyl compounds couple together to form a beta-hydroxy carbonyl compound, or the Claisen condensation, where esters link up through a similar mechanism to form new CC bonds. So yeah, enolates are one of the most powerful examples of carbon ion chemistry in action. Another important reaction involving carbon ion is the dissolving metal reduction of alkynes. This one's pretty cool because it selectively reduces alkynes to transalkenes using sodium metal in liquid ammonia, or Na over NH3. Here's how it works. The reaction follows a single electron transfer mechanism, or SET. First, sodium donates an electron to the alkyne, creating a radical anion. Then, ammonia comes in and protonates it, forming a vinyl radical intermediate. A second electron transfer, followed by another protonation, gives you a transalkene. And here's the interesting part. This reaction is highly selective for transalkenes because of the steric and electronic factors that influence how the intermediates behave. So overall, this just goes to show how versatile carbonates really are. They help chemists build complex molecules through nucleophilic additions, substitutions, and even reductions. Understanding how carbon ions behave is key, whether you're predicting reaction outcomes or designing better synthetic strategies. All right, that's it for today's lesson. I hope this breakdown helped clarify carbon ions and how they work. If you found this helpful, don't forget to like, subscribe, and hit the notification bell so you don't miss the next lesson. See you next time.